Good evening, guys. I'm going to go ahead and get started. Um, this is my chance to hopefully speak directly to some of you, answer some questions directly as well. Kind of our chance to meet occasionally as these live review sessions and so on and so forth. And I hope some of you get a chance to take advantage of this. And also, I hope it helps you when you have to, be out on your own working on the exam this coming few days. So I'm going to go over the material that starts where I stopped off on the last review session on Tuesday. We covered sessions 1 and 2, probability, types of variables. We talked about diagnostic tests, a whole bunch of other stuff like that. So I want to get now into distributions that involve binomial variables and numerical variables. Okay, so I'm going to start with binomial variables. And we've seen this already in the videos. We've talked about binomial variables. They're nominal variables that have two values. For instance, male and female, diabetic or not diabetic, and so on. Very frequently, we refer to the data where a person has the condition, or we find the condition that we're looking for as a success, and where we don't find it as a failure. Kind of a weird way to refer to diabetes, being diabetic or not diabetic, but it's kind of the way we do it. But the real factor here, the real key here is that there's two values to the variable. Okay, so I'm going to start with something like just simply heads and tails, flipping a coin. And we went through that. If you go back in the videos, we go through a probability tree where we start with a first coin flip could be heads or it could be tails. And then from there, you could get another head or a tail. And then from there, you could each get heads or tails. And we track through that, all the probabilities. And we found that in the end, that there was only one way to get 3 heads in a row, for instance, and the probability of that happening was 1 in 8 or 0.125, and only one way to get all tails, and that was also a very relatively low probability. But there was a higher probability of getting 2 heads and 1 tail, or 2 tails and 1 head. Okay, and that's because there were more ways for that to occur. So one of the ways you might look at this is if I were to say drop a bead, a ball bearing, down on a pin, right? That when it hits that pin, it hits it right in the middle, it could possibly go to the left or to the right. Equal likelihood that'll go either direction, just purely due to chance or whatever conditions were there at that particular moment. But it's 50-50 whether it goes one direction or the other. Well, if I line these pins up, going down into row after row after row, every time it hits a pin, it goes to the next pin. Kind of like if you've ever seen Japanese pachinko machines, right? Kind of bouncing back and forth like that. Now, let's say I have 10 rows of these pins. Well, I would expect the most likely outcome, just by chance, is going to be that I'm going to get 5 times to go to the left and 5 times to go to the right. So I would expect those balls to pile up in the middle the most. But then some of them are going to have, maybe an extra 6 turns to the left, and they might be a little less probable, but they might pile up. They might be the second likely possibility, as well as 6 pins to the right, and so on and so forth, with the probability of getting all left turns or all right turns being the least likely outcome. And I would likely see the least number of balls, building up in those ends. This actually becomes kind of a distribution that I can map, that I can calculate. In fact, there's a formula that we can use to describe all these outcomes, and I'll get to that in a second. Okay, and in fact, I can actually demonstrate this for you, but this is actually a probability diagram. And you'll notice that it's symmetrical. Very often it's going to be symmetrical, not always. And that half of the distribution is to the left, half of the distribution is to the right, and so on and so forth. Sometimes it'll be a bit different, but in this case, it's symmetrical. Okay, and it's bell-shaped as well. Kind of like something we're going to discuss later on, the normal distribution, but that's not the same thing. It's a different kind of distribution Mathematically, it's different. The shape is, although it's bell-shaped, also it's also symmetrical about the middle, about the mean. It's used for numerical variables, number one, and its properties are a little bit different. Okay, but we certainly have something that kind of like mimics it. In fact, we may also if we get a chance tonight, talk about how you can actually make some assumptions about this and apply some of the same rules as the normal distribution to this thing, which is called the binomial distribution. Okay, I just want to show you that this really works this way. And then show you by doing this. Okay, first of all, number one, there is a machine that exists that does exactly what I'm describing. You can see a version over here. It's called the Galt machine. I'm actually going to play a little video for you. This is on, I think this is in session 3 most likely. If I play this video, you'll see that there's the device, and it's actually dropping balls down there, hitting pins going left and right and left and right, and so on and so forth. And let's see if our prediction about how this outcome will be distributed actually matches in the real world. And in fact, there you go. There it is actually in real life, distributed exactly the way that we were talking about it's being distributed. Okay, so that's the binomial distribution. By the way, this machine is one of the demonstrations that they have at Queens, in Queens at the Hall of Science. If you have a kid or something like that, even yourselves, they have a million hands-on demonstrations in math and geometrics and optics and mechanics and stuff like that. You'll have a great time there. It's really a great place. But this is actually a demonstration of that the binomial distribution operating in real life. So at any rate, getting back to this. Okay, so now there's a formula that actually represents this distribution that I can show you. And you can either do you can use one of these trees, these probability trees that I discussed before, that we've discussed before in the videos and so on and so forth, or you can actually apply a specific formula to it. Not that one. Here you go. Here's the binomial distribution formula. Okay, and this basically is a calculation of all the different probabilities that might occur given the probability of your outcome. And in our case, the probability of the outcome that we're working with, heads or tails or left or right, is 0.5. If we're talking about a population of diabetics, there's a 10% prevalence of diabetics. Probability of any particular person being diabetic would be 0.1. So P would represent that 0.1. Q would represent 1 minus P, which is 0.9. And X would represent the number of successes, right? Number of people that have diabetes. And N represents the number of trials. So basically, for instance, if you were talking about what's the probability that you would get 3 people out of a sample of 10 randomly selected from a population with a prevalence of diabetes of 10% that would have diabetes, 3 out of 10 having diabetes, exact probability of getting exactly that. You put the 3 factorial in here and 10 factorial there, 10 factorial minus 10 minus 3 factorial, p to the 3 times q times, which is 0.1 to 3, 0.9 to the 10 minus 3 or 7. And you solve that. It's pretty tedious calculation, especially if you start getting into sample sizes that are even bigger than 10. And you could wind up with some that are much larger than 10. I'm going to show you a much more basic way of calculating that, a more practical way of calculating that uses a function in Excel that you'll be able to use to solve some problems. And I see I got some of us online now, and hopefully you guys will you can see my screen and you can hear me chat, you can hear me talk. If you can, just type into the chat box so I know that you're able to receive this. If you have a microphone, since there's only a few of you, if you have a microphone here on your computer or whatever, I'll turn your mic on so you can actually interact with us and speak or ask questions of like that. Otherwise, I'll just glance down at the chat box every once in a while if you have a question. Okay, so let's take a look at this binomial distribution. I made up a summary of some of the exercises that were in the session 3 and session 4. So I'm going to start with this first one, the idea of this binomial distribution and applying situations where I want to solve problems using binomial distribution. Okay, a study indicates that 10% of nursing homes are diabetic. Nursing home patients are diabetic. You randomly sample 10 patients. Surprise, surprise. What's the likelihood that exactly one will be diabetic? What's the likelihood that 2 or fewer will be diabetic? What's the likelihood that more than 4 will be diabetic? Or what's the likelihood that 4 or more will be diabetic? Sounds like word problems. I have to interpret these things as well. Well, that's certainly true. So let's take a look at this binomial distribution function in Excel, which is a substitute for that formula that I just showed you. I'm going to blow this up a bit bigger. Let's make this 250. Okay, good. It's easier to see. Okay, so let's see. If we sample 10 people randomly out of this population, the probability, number of outcomes, the outcomes that we can get is that 0 people are diabetic out of the 10. 1 is, 2, 3, 4, 5, 6, 7, 8, 9, or possibly even all 10. Well, since the prevalence is 10%, I would assume that, or maybe I'll ask you, what's the most, if the prevalence is 10%, and I'm randomly sampling 10 people out of this population, what's the most likely outcome for the number of people that are diabetic? Anybody want to hazard a guess? 1. Exactly right, 1. So I'm gonna test that right now. I'm gonna test what's the probability of getting exactly 1 person out of 10 that's diabetic. And I'm gonna go in here and I'm gonna say equals, and the function is binom dist. There's a few. I think there's binom dot dist. It's really the same function. I'm just going to use binom dist. Excel prompts me for the information that it wants. Number of successes. That's the number of people that are diabetic. That's going to be equal to 1. I'm going to plug that in there instead of actually calculating it. Comma. Number of trials. Number of trials is the number of people in the sample. That's 10. The probability, which is the same for every person that I in the sample, is 0.1. Comma, and then there's another factor it wants, which is cumulative. For the moment, I'm going to write false, and I'll explain that in a second and hit enter. So the probability that I would get exactly 1 person who is diabetic out of 10 is about 38.7%, 0.387. Okay, so that's makes it pretty likely, but that means it's more likely that I'll get either less or more people than 1 person, right? So that's not the only possibility. So let's take a look at 0. Do you guys think that this is going to be bigger or smaller than 1? Kind of answered that question already, didn't we? Right? Binom dist 0, comma, 10, probability is 0.1, and false, close parentheses. It's smaller, isn't it? Just as we would expect it, right? Exactly, we'd expect it to be smaller, right? And I'm going to drag this down. I'm going to find all the probabilities for all of these different possible outcomes. And the further away we get from that 1, from the most probable outcome, the smaller the probabilities become. When Excel uses an E to dash something, it's using scientific notation. That's 3.645 times 10 to the minus 7. In fact, the probability of getting all 10 people that are diabetic is like 10 to the minus 10. It's like enormously, tiny, tiny probability, right? 0.00, 9 zeros and 1, right? So very, very, very unlikely. So with lottery winning odds, actually. So now that's very interesting. But we just answered one question here. What's the probability of getting exactly 1 diabetic? What's the probability of getting 2 or fewer diabetics? Well, 2 or fewer, it looks to me like these various outcomes are exhaustive. These are all the possible outcomes. So if I take the sum of all these, I would expect that it's going to add up to, of course, 1. And indeed it does. Okay, so if I want to know what's the probability of getting 2 or fewer people who are diabetic, well, I'm thinking I could just say it's simply the sum of the probability of 2, 1, and 0. and 93% probability that I would get 2 or fewer people who are diabetic. Well, how about if I ask myself, what's the probability of getting more than 4 people who are diabetic? Well, more than 4 people, well, 4 wouldn't be included in more than 4, right? Only 5, 6, 7, 8. So more than 4 is going to be equal to the sum of all of these. Okay, still not very likely, but because the prevalence is so low in this situation. And 4 or more who are diabetic. Well, 4 or more who are diabetic. Before I do that, I'm going to show you something else I could do. Let's say I wanted to know how many, what the probability of getting 3 or fewer people who are diabetic. Well, you just saw me do that with the sum. Sum. Okay, the probability of getting 3 or fewer is almost 99%. Another way I could do that calculation without having to do all these others, I could say equals binom dist, parentheses, and again I'm going to use 3, comma, 10, comma, 0.1 for the probability, comma, except this time for cumulative, I'm going to put true. And it's going to give me the probabilities for all 3 and all the other probabilities before it, all added together. In other words, the sum of all those should come up to 0.9872. And I'm going to hit enter and cross my fingers. And indeed, it works. So that's another way that you can use. That's the distinction between true and false. For cumulative, true, false only gives you that specific outcome. True gives you that outcome plus all the ones that have fewer successes as well, including 0. Okay, so now the next question was, what's the probability of more than 4 people, or 4 or more people who are diabetic? Well, 4 or more people would be all of these people, 4 or more, right? More than 4 would be this. 4 or more would be all of these people. Well, I already know the probability of getting these outcomes, right? So since that's that number, why don't I just simply take that number, subtract it from 1, and that will give me the remaining probabilities for all of these. And in fact, I could do that again and just to make sure, just to show you it's really going to work. Okay, there we go. It worked again. It's my lucky day. Okay, so I'm going to leave it to you. I'm going to move on, but I'm going to leave it to you to play around a little bit more. I'll post this on Blackboard. You can play around with it as well. Okay, so that's binomial distribution. Now I'm going to move on to the normal distribution. There are many numerical functions that display the property of normality. A bell-shaped probability curve. This might represent a population, the BMIs of a population of college students, or it might represent blood pressures of people in New York State. It might represent many things, but many public health measures, biological measures, many of them exhibit a, if not a perfectly normal distribution, a near normal distribution. There are 2 things that influence the shape of this bell curve when we're talking about a normal numerical distribution. One is the mean of the distribution, mean of the values for the variable, and the other is the standard deviation. The mean locates the middle. The standard deviation tells you how spread out it is. But one of the things about these normal distributions is it doesn't matter for this normal distribution, right? For this normal distribution, it doesn't matter if it doesn't matter if, oops, I got this thing upside. I got my tablet upside down. That's why this is not working well. Okay, for a normal distribution, if I take a mean of 100, come on, right? Let's see what we got here. Mean of 100, mean equals 100, and I take a standard deviation of 10. I'm using population values here, mu and sigma for our purposes right now. And the mean is 10. My distribution is going to be bell-shaped. If it's normally distributed, it's going to be bell-shaped. The middle is going to be 100, right? And almost all of the values are going to be within 3 standard deviations. above the mean, right? Standard deviation represents a value of 10. So 70 is 3 standard deviations below the mean, and 133 standard deviations above the mean. Now, if I were to take that same mean, and I said that standard deviation is equal to 2, my distribution might look something like this, right? Much narrower. Same middle, but much narrower. And my width, almost all the values for whatever it is are going to be between, say, 94 and 106, right? So it's not narrow, but it's still bell-shaped. It's still symmetrical, right? And the mean is in the middle, okay? And similarly, if I had taken a different number for mean, I might have a totally different shape, right? But still have all those properties. Well, every one of these normal distributions has properties where there's a relationship between the mean and the standard deviation, where the standard deviation will describe for us the distribution of all the values within that population, or if you want to look at it differently, the probability of finding an individual within that population that is in a certain area of this distribution. Okay, and this is called the empirical rule. Okay, empirical because it's just an estimate, right? And basically, we can estimate that about 68% of the values are between 1 standard deviation below the mean and 1 standard deviation above the mean, right? 95% of the values are between 2 standard deviations below and 2 above. And almost all of the values, 99.75, are typically going to be between about 3 standard deviations below and 3 standard deviations above. This is really kind of asymptotic, so you never really say it's 0, but almost all the values are going to be within 3 standard deviations. You can also look at it from another perspective, that these represent probabilities. That's the probability of choosing an individual that's within 1 standard deviation below the mean and 1 above the mean is about 68%. The probability of choosing a random individual from this population, bing, 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 choose a random person from this population between 2 standard deviations above and below, in this case between 80 and 120 for that distribution, is 95%, and so on and so forth. Okay, so that's of some interest to it because it helps us understand how these numbers are distributed, how these values are distributed, what the probabilities are of the outcomes when we sample populations, and so on and so forth. Okay, so I'm going to move on from there, and I'm going to take a look at this, maybe a problem or two that uses this empirical rule. Okay, let's say, assume the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Okay, what's the probability that a randomly chosen individual is greater than 68 inches? I'm not even really going to need a piece of paper to do this, am I? Okay, the mean is 68 inches, the standard deviation is 4. What's the probability that a randomly selected individual from this population is going to be greater than 68 inches? Take a guess. 50%. Right, exactly, because that's the mean, right? The mean is in the middle. So if I look here, if I did this here, okay, I'll sketch my distribution. You know, it also always does, if you're going to do these problems, it doesn't hurt to sketch these things. Makes it a little less likely going to make error. So your mean is equal to 68, and the standard deviation is equal to 4. Right? What percentage of the population is greater than 68? Well, half of the population. The mean divides this standard normal distribution in half. Right? So 58% of the population would be greater than that. Okay, how about between 64 and 72 inches? Let's say 64 and 72 inches. Okay, well, how many standard deviations below the mean is 64? That's 1 standard deviation below the mean. 72 is 1 standard deviation above the mean. So what percentage of the population is between 64 and 74 inches tall? I know you guys know this, right? right? What percentage is between 61 standard deviation below and one above? It's going to be 68%, right? About 68%. Okay, how about this next one? Between 70 and 76 inches. I'm sorry, between 60 and 76 inches. 60 and 76 inches. Right? Well, in that case, we're now 2 standard deviations below the mean and two standard deviations above the mean, plus 1 and plus 2. 2 standard deviations above the mean. So this is going to represent 95% of the possible outcomes. In other words, the probabilities of us choosing a person that's going to be between 1 standard deviation above, below, 1 standard deviation above is 68%. Is 95%, excuse me. Okay, so I'm gonna move on to the next one here and just do another quick one here. Okay, good. I like this one. Okay, I want to do this one. Okay, gestation time for humans has a mean of 266 days and has a standard deviation of 25 days. Okay, what's the percentage of pregnancies that you would expect to be greater than 291 days? This is 291. But we're interested in the proportion of pregnancies that are greater than 291. Well, 291, how many standard deviations is that above the mean? Well, let's see, 291 minus 266 is 25. So that's 1 standard deviation above the mean. Well, I didn't tell you too much about what's over here, right? I did say that 1 standard deviation below, 1 standard deviation above is 68%. So between the mean and 1 standard deviation above, since they're symmetrical, we would expect 34%. So we would expect that that would leave for this area above 1 standard deviation approximately 16% of the possible outcomes. So that's a probability of 16% of the pregnancy being greater than 291 days. How about 241 days? Similarly, 241 days, where'd it go? I lost it. Let me get that back. There it is. Okay. 241 days. Right. And similarly, that's 1 standard deviation below. Right. So it's going to be 34 also. And the probability of a pregnancy that's less than that is, again, 16%. What's the probability of pregnancy being shorter than 241 days or longer than 291 days? We just add these two together, and it would be 32% probability of that, of one of those outcomes. Okay, pretty simple. Can get a little bit more complicated depending on how specific the directions are for what areas of this distribution that we're going to ask it for. Now, the next issue that we're going to run into is it's not always going to be an even number of standard deviations. Take a look at this problem. The heights of US women have a mean of 63 inches and a standard deviation of 2 inches. I'm going to sketch that out. Okay, let's see. Okay, so, okay. So what was our mean? Our mean was 63 inches, and our standard deviation was 2 inches. Okay, so what's the percentage of women that you would expect to have a mean height, or the probability of choosing a woman as mean height, less than 63 inches? Well, that's easy, 50%, right? Less than 62 inches. Oh, okay, less than 62 inches. Okay, maybe we can use our empirical formula for 62 inches. Well, wait a second. This distance is the standard deviation is 2. This is only half a standard deviation below the mean. So our empirical formula is not going to be very extendable to this. Right? It's not going to be very easy to apply that to this. So how many standard deviations below the mean exactly is this? So we're going to call the number of standard deviations above or below the mean. We're going to give that a definition, call it a z-score. The z-score is equal to the difference between the mean and the value you're interested in, x minus mu, over the standard deviation, right? Makes sense, right? Because it's just the difference, how far away it is over the number of standard deviations to give you the number of standard deviations. If this had been 61, it would have been, if this had been 61, it would have been 63 minus 60, 63, 61 minus 63 would be minus 2, over 2 would be minus 1, would be negative 1 standard deviation. In this case, though, we're not so lucky. It's 62 minus 63 over 2. That's equal to minus 1 over 2, or minus 1/2. Right? So our z-score is equal to 0.5000, right? So now, excuse me, negative 0.500. So now we need to find some reference that'll help us calculate what this area is here. Well, one of the ways we could do that is we could solve this equation, which represents this probability function for the normal distribution, which represents this line which traces the probability of all the possible outcomes in this normal distribution. Of course, nobody will want to take this class if we had to do that. So there's got to be a better way, right? So the better way is we actually have a table that's been prepared based on what's called a standard normal distribution. That formula has been solved for a standard normal distribution where the mean is equal to 1, excuse me, mean is equal to 0, and the standard deviation is 1. So you could see, but so that they could calculate efficiently the areas for all the different z values that you might have. The way this table works is that the z-scores are listed here in this column, and the area under the normal distribution, the probability under the normal distribution, is this grayed out area. So our z, whatever z-score you look up in here, these numbers in the middle will represent that area, that shaded area. And the z-score is always going to be represented by the area to the left of the z-score, right? So it's kind of cumulative, the way that the binomial distribution function in Excel was cumulative. Okay, so, oh, by the way, thank you for keeping up with a couple of answers and stuff like that there. Especially if I make a mistake, like let me know about it. So at any rate, this area in here is what we're really interested in. So in our case, we're interested in a negative z-score. Negative z-scores are the scores that are to the left of the mean, because x minus mu is always going to be a negative number when it's to the left of the mean, right? Because 62 minus 63, right? But if we're on the right side of the mean, and you'll notice that the highest area that we get with a negative number is 0.5. And if we have a value on, like if we were looking at 64 instead of 65 instead of 64 instead of 63, we would have been plus 0.5, because it would have been 64 minus 63 is positive 1 over 2, or plus 1/2, and we would have been on the right side of the normal distribution. Well, if the z-score is on the right side, you can see this area encompasses everything from that point on. So it's going to, all these numbers where it's a positive z-score is going to be greater than 50%. And you can see the lowest number here is 50%. So I'm going to look at our z-score that we want for our purpose, which is negative 0.5. Negative 0.5, well, there's 10 columns of numbers here. Which one should I choose for a z-score negative 0.5? Well, the reason why there's 10 numbers is because very frequently we're going to be working with another digit for the z-score. Maybe the z-score had been 0.52, right? What these columns represent is that third digit. This column is 0, 1, 2, 3, 4 after that initial digit. So a z-score of negative 0.50 would be this value here. A z-score of negative 0.54 would be 0, 1, 2, 3, 4 would be this value here. And these represent areas to the left of this z-score. So the area to the left of our z-score is 30.85%, or 0.3085. So I'm going to go back to my table. And the area to the left of that is 0.3. The area here is 0.3085. Okay, so now what was the question again? Let's go back here and see what that question was. Right? The question was, what percentage of women, so in other words, probability, they would expect to have a mean a height that is less than 62 inches. So our 30%, 30 odds percent is going to be our answer for that particular question. Okay, what's the next question? What's the probability of having of selecting a woman at random, or the percentage of women in the population that have a height greater than 66 inches in this population? Well, 66 inches would be up here. And what's the z-score for 66 inches? Well, it's going to be equal to 66 minus 63. And you can probably figure this out in your head. But it's going to be equal to 1.50, right? 1.5. That's a positive 1.5. Let's go back to our table, right? Our table set for 1.5, positive 1.5. We're going to use this one. Positive 1.5, 0 is 0.9332. 93.32. So 0.9332. Well, let's be careful though. That is the area from here down, right? Remember, it's cumulative from here down. The problem was asking what's the probability of having a woman that has a height greater than 66 inches, right? So this area is 0.9332. The area of the entire distribution is 1 or 100%. Right? So the area that's left here, that is the answer to the question, is 1 minus 0.9332, which is 0.668, probably, right? That looks right, I think. Somewhere around there. Okay, 0.0668. Okay, so you can see that this can get a little tedious, right? Because you got to be really careful with what areas that you're talking about. Okay, I'm going to move on. I'm going to move so we covered as much as we can. I'm going to move on a bit again now. And next thing that we have in the videos and in the various materials that we have on Blackboard. I got to take a drink. My voice is getting kind of dry. I'm going about a mile a minute here. I know. I fear that I'm going pretty fast for some of you guys, but I know some of the people that are on right now, and I know that they are pretty capable of keeping up with this. Okay. Okay. So now let's talk about something new. We very frequently, I just was talking about, well, here's a distribution, and the mean is equal to 200, and the standard deviation of the entire population is equal to 10. Well, it's pretty noble of me to talk like that. But chances are, we never know what the mean of the population or standard deviation is. Right? The only place we might know is when they do a census, and they only do that every 10 years, and only, excuse me, only collect certain kinds of information. For the most part, we never get to know what the true mean is of a population. We depend on samples. Right? In that case, we're talking about X bar and standard deviation. We depend on samples to give us an approximation of the mean and the variability within the population. Okay, so we got X bar, we got standard deviation. And of course, the sample size is going to impact this somehow or other, as we're going to see in a minute. So at any rate, so now let's take a look at the properties of sampling. Okay, and there's a video that involves a demonstration where you actually do some sampling from a large group of numbers, random sampling, and create new samples and so on and so forth. But I'm going to summarize that by telling you that if I have a population like this, that literally, I'll use the one I just did, has a mean of 200 and a standard deviation of 10. And it looks something like this, right? I would expect the mean middle be 200. 3 standard deviations across would be 170, and 230 is going to be spread out kind of something like that. Now, if I were to take a sample of, a sample of size 25 from this population, I would expect that when I take the average of that sample, right, I wouldn't expect, I would expect that I take a sample of 25, I wouldn't expect that average to be 170. I wouldn't expect that average to be 230 because I'm randomly sampling 25 people. I would have literally get 25 people, be unlucky enough to get all 25 people that are 230 or 170. I would expect it to be reasonably close to the middle here somewhere. And the bigger sample, the more likely it's going to be close to the middle. Well, in fact, if I were to make believe that I took a sample of size 25 from this population and I wrote it down, let's say the first one I took one and it came out to be 199, pretty close to 200. Let's say I did it again, 25 people, I did it again. This time wasn't quite as good, it came out to be 196. And I did it again and it came out to be 204. And I did it again and it came out to be 202. And I did it again and I got lucky, got 200 and so on. If I did this an infinite number of times, or many, many, many times, and I took these means and I made a new distribution, which was a distribution that was of all of the results of these means of samples of size 25, this new distribution, now take a look, no, some are more than 200, some are less. This new distribution would also have a mean of 200. But it would not be as variable as my population is, simply because the numbers are all going to be closer to the middle than my actual population. And the relationship here between the standard deviation for the population and the standard deviation for my samples is my standard deviation for my samples. I'm going to call it a standard deviation is equal to standard deviation of the population divided by the square root of the sample size. Right? So my standard deviation of all my sample outcomes is going to be equal to 10 divided by the square root of 25, which is 5, is equal to 2. So I would expect my samples to be in the range of 194 to 206, right? A narrower range. And in fact, what if I had taken 100? My sample size were 100, then it would be 10 divided by the square root of 100, which is 10, and this is 2, and my standard deviation would be equal to 1. Okay, so it would make a distribution of samples even narrower. So one of the things I might notice when I do this is that if I know the population standard deviation, or if I guess at it, if I think I know enough about it to guess at it, for whatever reason, right? Then if this is my population, I'm going to call that new standard deviation of all the samples, I'm going to call that the standard error, right? So if our population mean is 100 and our population standard deviation is 10, then I'm going to work with samples, the sample size equal to 25, right? But then my standard error, as I just figured out, was going to be equal to this. It's going to be equal to sigma over the square root of n, which is 10 over 5, which is equal to 2. So my standard error is equal to 2. So I know by the properties of the normal distribution, I know that 95% of my outcomes are going to be between roughly 2 standard deviations below and 2 standard deviations above the mean for my samples, okay, or my population for that matter, right? Mean is 100, right? So 2 standard deviations below, 2 standard deviations above. So 2 standard deviations below would represent a number, let's see, standard error is 2, that would be 96, and this would be 104. Well, I would expect 95% of my sample results to be within these two numbers. So now that gives me a window on understanding how likely it is that I would be off by a certain amount in predicting the true population mean based on samples that I would take. And in fact, we use this knowledge. I'm not going to go too much, and I'm not going to really go over it too much because they got those other videos that are online. But based on this information, I can say to myself, I think I could say to myself that that if my sample, let's say my sample comes out to be 99, I take a sample of 25 people in this population, sample comes out to be 99. I make, let's say I know the standard deviation of the population. I'm able to calculate standard error for the moment. I'm going to say to myself, if I know if my sample came out 95, I'm feeling that I could say to myself, there's a margin of error that I can add to this 99, the spread on either side, to tell me what the likelihood, give me a range within, I can say with 95% certainty that the true population mean lies. Okay, so I'm going to take advantage of it. I'm going to say, okay, so from now on, my confidence interval, what I'm going to call my confidence interval, for 95% certainty, right, is going to be equal to whatever my mean is, x bar, plus or minus the standard error, right? Excuse me, not standard error, but two, right? It's two standard deviation, two times the standard error, right? Whatever the standard error is. Okay, that's going to be my range for my confidence interval. So in this case, it's going to be 99 plus or minus 2 times 2, which is 4. So I can say that I'm 95% confident that the true population mean lies between 95 and 103. That's my 95% confidence interval. Okay, that of course means also that you have 5% chance of being wrong, and the true mean lies outside of that. But that's a prediction that I can make now. That I gave you a little bit of a shortcut. You use the empirical formula to determine 95% of the outcomes are between two standard deviations below the mean and two standard deviations above the mean. In reality, it's not two standard deviations. A more exact measurement would be, well, let's see what area represents. If we're talking about this in that vein, let me go, nope, look back. Okay, I'm going to bring this back to our lightning round here. If this is the middle 95%, that means that there's 5% left outside of that middle section, that middle range of possible outcomes for the mean, in the mean of my samples, right? Well, that 5% is divided between the lower tail here that's outside of it and the upper tail here. So this lower tail and this upper tail, they're both 2.5%. Right? So if I want to know what the z-score really is, not 2, but what it really is, I would have to find what's the z-score that's closest to an area of 2.5% at this end. Okay, so I'm going to go here to the negative ones, and I'm going to look for an area that represents 2.5%. 2.5, right? And it looks like it's 1.96. So instead of using 2, for a 95% confidence interval, we're going to use 1.96, right? And as it happens, as we move forward, if we're looking for a 99% confidence interval, right, that's going to be wider, right? 99% confidence interval means we want to include 99% of the possibilities, so it's going to be a wider spread, right? So that 99% confidence interval is going to have a bigger z-score. The z-score for that is going to be equal to 2.58, I think. I'm pretty sure it is. Hope I'm not having a senior moment. I think we can look at the chart and make sure. And if I'm willing to have less of a confidence interval, 90%, that would be narrower, and that would be 1.64. You can actually look these up. And when you've been doing this for a little while, you'll remember these numbers all by themselves. Okay, so I'm going to ask you a quick question. Okay. Okay, I'm going to ask you a quick question here. I have a distribution whose mean is equal to, let's see, we take a sample We find an average. The average is equal to 200. And we determine that the 95% confidence interval is between 190 and 210. Okay? Would the 90% confidence interval be wider or narrower? Okay, what do you think? Would the 90% confidence interval be a wider interval or a narrower interval than, well, not 190 to 210? I'm going to wait for a guess. It's okay to be wrong. What do you think? Wider or narrower? I'll give a couple more seconds. Sometimes a little bit of a lag. Sometimes I've put everybody to sleep. Okay, I'll give it to you. The 90% confidence interval, right? 90% confidence interval is going to be narrower. Say 205. It's going to be narrower because you're willing to have more of a chance of being wrong. So you're willing to be, thank you very much. You're willing to have a narrower confidence interval because you're willing to accept a larger chance of being wrong and having the mean outside of that. Conversely, a 99% confidence interval is going to be wider, right? Because it needs to be wider to increase your confidence that you've captured the true population mean between those. And mathematically, that will always work out that way because your margin of error, the z-score times the standard error, for a 90% confidence interval, it's going to be 1.64. For a 95% confidence interval, it's going to be 1.96. For 99, it's going to be 2.58. So that number, that margin of error that you subtract and add to x, are going to get bigger so that your confidence interval will then get wider as you increase your requirements for confidence intervals from 95 from 90 to 95 to 99%. Okay, so that's kind of what we're after here when we're looking at confidence intervals. You can also do confidence intervals for binomial distributions. You can actually assume that the binomial distribution is similar or has properties like the normal distribution, and you can apply these to proportions as well. Proportion is really a binomial, right? Because proportion is, yes or no, voted yes, male or female, voted yes, voted no, voted for this, voted for that, and so on and so forth. So if you have a proportion, say a sample p cap, you can almost look at that as if it's the same as x bar, right? So our confidence interval for a proportion would be p cap, the proportion, your sample proportion, plus or minus, right, your z-score, right, whatever it is, times your standard error. And in this case, your standard error for a proportion is going to be equal to the square root of n times p times 1 minus p. Right? Sometimes they call this q instead. You'll see it as n times p times q instead. Okay, that you can use as your standard deviation, right, or your standard error, and your z-score depending on whether it's a 95% confidence interval, it's going to be 1.96, 99% confidence interval, right? It's going to be 99% confidence interval. It's going to be 2.58. Okay, so I'm gonna kill it there, and I think we covered really a lot of stuff right here. And I hope, number one, I hope it will, inspire you a little bit to go back and take a look at some of the material that we've been covering. Because from once we go to Monday, we're really going to break into real statistics. We're going to start learning about how to apply this to actual statistical tests, such as t-tests and chi-squares and so on and so forth. So the remainder of our lightning fast semester is going to really cover a lot of really hardcore statistics that in the future you're going to be applying to a lot of stuff. So hopefully I'm going to be posting the exam by tomorrow afternoon, let's say. You'll have until Tuesday end of day to complete it, and I'm hoping that you won't have too much trouble with it, and you'll do it on your own. You won't, that you'll have enough faith in me that I'm not out to trip you up and stuff like that. That you'll give it an honest try and do it on your own, and so I can get a measure of how well we're all keeping up with this material. Okay, can I answer any questions before you guys go off? You have a good idea like what we're looking for. Yeah, I'm purposely. I don't want you guys like, killing yourselves for a week and a half on, for 3 days solid. Doing this. I want to get a measure of how well you're picking the material up. I think the best way to do that is to limit it for 3 hours from the time you start, right? So I'm hoping that the material that what I give you won't take you more than an hour and a half or 2 hours, so that you can do it. You will need to. I haven't decided whether I'm going to ask you to do SPSS exercise, because I got a feeling some of you are still struggling with getting online with it or getting access to it. I may just give you some SPS outputs and make you interpret them, or maybe I'll do both. Maybe I'll do both, and then like if you don't have SPSS, I'll accept some sort of excuse or something. But I'm hoping that we have a chance to get some feedback on this exam, and then maybe the next exam we'll do differently or something like that. Give you more time or more options on it. It's going to be about 2 hours worth. Going to be about half of it's going to be about short answers or multiple choice and so on and so forth. Things like the in session one of the review session, I went over how to interpret that president's bar graph. Would be something like that. There'll be some stuff about interpreting variable types, nominal, numerical, and so on and so forth. There'll be something in the way of it. Also, half will be multiple choice. The other half will be, some sort of problems, like for instance, problems involving diagnostic tests, similar to the material way we went over it in the videos and on the review session. And then on this material, you saw some questions I put up there. I might make them a little bit more involved than what we used to demonstrate this here, because you'll have a little bit more time to work on them on your own. But again, I'm not trying to trip you up or hang you on here. I want to limit it to 3 hours, so you don't get too involved with it, and then I get a better measure of where we are. If necessary, and some of you really get tripped up on the exam and have get a horrible score or something like that, I'll figure some way that we can work out so that you can recover from it. But I think it's important that at this point, which is almost halfway through the semester, our quote semester, our lightning fast semester, at some point, at this point, I think it's important to me to see how well you're keeping up with this material as we get into more involved stuff going forward. It's going to cover sections one. It's going to cover sessions 1 through 4. That's correct. Even though the last session, the homework is due a little bit later, it will cover some material. In fact, we just talked about stuff from there, right? This confidence interval stuff is from session 4 mostly. But like I said, it's something that you'll have a chance to play around with. Just try and block out a little bit of time so that you can have an opportunity to sit down and work on it through those 3 hours. If it gets bollocksed up or something like that, or you get logged off or cut off or something like that, just email me and I'll find a way to get you logged back on or give you a little bit more time to complete it, past Tuesday if things really screw up. Okay, so I'm sorry I don't get to meet all you don't get to see all your faces and stuff like that, or get to talk to you. Even now, I was hoping that maybe some of you had a microphone that we could chat back and forth a little bit, because it would be easier for me to get some feedback from you. But we'll see where we are. We'll do the test. We'll see where we are next week. And I graded most of the stuff, assignment ones and whatever else I could find that was gradable on Blackboard, so you know where you stand there. And of course, if you submitted the homework, you have the opportunity to go back and redo it again, to raise your homework grade. So don't worry too much about the exam, because that 40% of your grade on homeworks is really going to buffer a lot of any issues that you've been winding with on the exam, especially on this first exam, because we have a little bit of time to recover. At the end of the semester, I'm going to send you guys a link to a video by a comedian from the 60s or 70s, in which he he talks about starting a university that he calls the 5 minute university, in which you go to the university for 5 minutes and you get a degree. And his theory is that basically all you're going to remember after 5 years after you've been out of school is what he can tell you in 5 minutes anyway. So for instance, economics, you take a class in economics, supply and demand. That's the end. That's the class. That's the end of the class. Once you've heard that, because that's all you're going to remember in 5 years anyway. So at any rate, it's a 5 minute university. I'm going to send you a link to that because that's kind of what this makes me feel like, because we're going through this material so fast. And I'm sorry I don't get to get you guys for 16 weeks during the normal semester. So anyway, so good night and good luck on the test. And I'm sure we'll get through this stuff. Session self-tests, are they still graded on completion basis? See how we are doing. Oh, the self-tests, the self-tests are for two reasons. One, for you to see your own progress, and me to be. See, it's very hard. Although I can kind of go on there and see how many people have seen it, viewed a video and stuff like that. I can't tell how, if that's one person or 10 people and so on and so forth. But those tests, as you go through them, if you do them, I know that you are halfway through session 2, or you are 3/4 of the way through session 3. So they're good for you because it kind of gives you an idea of whether or not you really understood the material you saw up to that point. And it's good for me because then I know if you're keeping up with the material. You kind of freaked me out. A lot of people freaked me out there a week ago because a lot of people were behind on those things. But you guys have done a really great job of catching up in the past week. So they don't actually affect your grade. Only the homework assignments, the exams, the class participation, which is, I wish you guys would spend more time on the discussion groups, exchanging information. Even for the exam, as long as you don't discuss specific exam problems, if you want to discuss how to use SPSS or how to find confidence intervals or something like that, in general, I have no objection to that. Just don't discuss anything specific about the exam, any specific problem on the exam. But I wish you guys would do that because in previous semesters, students have made really good progress with that. They've really started a dialogue, and I think they did a really good job of helping each other get through the material. And also, it means you get a more immediate answer. I try and get on there every day to answer questions. Sometimes it takes a little. I'm away for more than a day for whatever reason. But sometimes you got 20 or 30 students in the class. Someone may answer your question within minutes rather than waiting for me to get to it in hours or a day or something like that. So, and also I use that kind of as I use that and other stuff like maybe even the quizzes or something like that as kind of like a judge for that little bit of points that you get for class participation. So use those discussion groups. I think in the long run that you'll find them really useful. Okay, so good luck, guys. Take care, and we'll see how we get through the weekend and where we are next week after we get a look at the test. Okay, take care. Bye.